I try to make this a quick video, a response to Huygens optics regarding diffraction mostly, but interference and light and what is the cause and how it affects telescopes and apertures specifically. So we're talking about two ways of viewing what light is, the wave in medium theory versus the individual quanta of energy at a frequency. So the distance between the clumps of momentum would be the frequency versus some notion of waves and two electromagnetic fields, electric fields and magnetic fields oscillating and all of that complexity. So the simple circumstance is you have a surface of some kind and light is going to come through the surface, and yes, the waves are in their view this way. I'm arguing for a ray theory, so the rays of light are just little straight line paths with bits of energy at a frequency. And the argument is that what happens on the surface is that it's coated or covered with electrons, and electrons do what electrons do, right? I could draw it way over here maybe, okay. And when the photon interacts with the electron, it causes the electron to move, okay. So the photon hits, imposes some momentum on the electron. The electron already has a little bit of a jiggle, so it converts that momentum into a new direction. So essentially every interaction between a photon and an electron, the elements, the photonic elements, the quanta, causes it to be redirected in its path, like scatter. It will leave at any angle that's in the forward direction, any possible angle that's in the forward direction. It's probably likely that it's more probable that certain angles, so you would say it's more likely that the angles are this way and this way or something, but at any rate, it causes a scatter. And that's happening at the surface. So light that's coming in with a frequency, okay, pulses of volume, interacts with the electrons and it scatters in all directions. And so now it's some percentage of the light. So most of the light goes through, doesn't get affected. Some of the light gets broken essentially. And this also has to do with polarization. So if the light's polarized, which means that it's in a sequence, something like that, traveling through space, these would be the straight lines. Part of the light can hit the surface and be absorbed, and part of the light can be scattered. And what you're really just saying is from these point sources, okay, from the 2 point sources, there's at any point you can draw lines that'll end up being a wavelength of difference, and those would be your interference patterns. So it would just be taking the phase of the photons and just saying you're going to take one photon's going to scatter that way, another photon will scatter that way. They're all scattering in different directions. So the energy's still hitting all these places. It's just not in phase, and it can't be recreated into a photon. So what you're really basically saying is you're going to take one element from one surface and another element from another surface, and you're going to remake a photon out of those elements. So this element will provide the first element, let's say, and this one will provide the next element, and then this one provides another element here, and then you could say this one provides another element here. And so you're recombining a photon out of photons that were provided from two different sources, and you're just remaking the phase. And it's a 50-50 chance. You have a 50-50 chance of putting the pieces back in phase or having pieces out of phase. And that's all the interference pattern is made out of. The fact is you're just taking broken bits, scattered bits of heads and tails, so to speak, pennies that are in a pattern, heads or tails, and you're just saying throw them against a wall, and you have a 50-50 chance that it'll be heads tails, or it'll be tails tails, or heads heads, or heads tails. Okay, that'll be HT or TH would be the same thing, and obviously HH and TT. So it's just a probability equation. So yeah, you get bands at the point is just deciding, which one is the path length difference is deciding whether they're back in phase or out of phase. And it explains why that scatter from these points destroy your optical resolution, because they're throwing a bunch of light that was coming in any direction. So theoretically, I got room here, I got room up here. Okay, let me move the camera down. And then I'll have room at the bottom. All right, so the light can go into the circumstance from any direction, okay, the slits, and it can leave in any direction. So obviously this light is absolutely useless in terms of giving you any optical capacity. So any optical capacity is complete. This light is just wiping it out. These extra photons are just taking what you're trying to see, which is these two objects, and it's just basically making a mess out of it. It's just casting a bunch of noise on top of that image. And so the more, the closer those slits, the more noise. The further away the slits, the less noise, right? So the greater your aperture, the less noise you're creating per percentage of the light that's going through. And the smaller the aperture, the more the noise is wiping everything out. Because the percentage of light, I mean, obviously, the percentage of the light that hits the surface or gets affected by the surface is increased as you make the surfaces closer together. So obviously, in this circumstance, lots of the water goes through without being affected. In this circumstance, 50% of the water gets through and 50% is affected by the surface. So you're just changing the percentage of the light that's getting affected by interacting with the surface. So this model completely can explain the phenomenon, okay, without any necessity of creating anything called an electric field or a magnetic field or any of that stuff, and explain partially why photons are inert to those electric and magnetic fields. They're not bent by them. So they obviously don't really have a charge component, and the only thing they're being affected by is the electron itself, but the electron is only changing the direction. And you could also understand this as being one of the reasons for the redshift of light. So the more it's traveling through space, the higher the odds are it's run into an electron in the form of a hydrogen atom. And it's hit that electron and scattered off of it. And the scatter causes a tiny shift in the wavelength. So for every scatter event that takes place, the frequency is lengthened, a little bit. So for every scatter event, the frequency is widened a little tiny bit. You can think over billions and billions of years traveling through space, the light's going to be more and more likely to be scattered. And then likewise, the light that was coming from hot areas of the universe is likely to run into a lot more of those molecules and therefore scatter more and also have less resolution. So that by the time some of this light can actually get to you, it's not necessarily going to be traveling a straight line either. It's not only going to be redshifted, but it's going to be pretty noisy. But anyway, that's a whole nother subject. So I just want to keep this brief on the, on the idea that the wave Huygens theory it's got a lot of nonsense in it. Infinite number of point sources. I mean, you shouldn't go for anybody shouldn't be falling for the infinite number of point sources. And there is a practical way to understand light as quanta of energy. And you're really just saying it's heat. It's really just heat at its precise frequencies, and that's it. It's just energy at a precise frequency. And we can see some frequencies and we can't see other frequencies with different instrumentality. And the frequencies can be broken and reconstructed pretty simply. So anyway, we'll leave it at that and see if there's any response and such and so forth and whatnot. Thank you for your attention and such and so forth. I guess I could do this just to I'll do that just for fun. Okay, the end of the video. Thank you.